Hello everyone, welcome to the lab explanation video for Lab 2.1, Image Classification with Convolutional Neural Networks and TensorFlow. In this lab, we are going to be exploring the foundations of convolutional neural networks, as well as one of its practical uses in image classification. More specifically, we will be creating a convolutional neural network in order to classify handwritten digits images from 0 to 9. At a larger scale, a model like this could be implemented in order to analyze the zip codes in order to increase efficiency in the logistics and transportation industry for services like mailing and shipping. To access this lab, you can go to the inspiredk.org website and click on the AI Program Labs button. This will take you to the inspiredk.org GitHub, where you can further navigate to the MIT Intro to Deep Learning repository. The lab we are going to be going through today is adopted from the MIT Introduction to Deep Learning course, and I edited it under the MIT license. Once inside the MIT Intro to Deep Learning repository, you can navigate to the Lab 2 folder and click on the Lab 2.1 Image Classification with CNNs and TensorFlow Python Notebook. Inside of the Python notebook, you can click the Run in Google Colab button in order to run this lab and go through it on Google Colab, a free service offered by Google which allows anyone with a Google account to access high-power processing units. Now let's dive into the lab. Before starting the lab, I want to make sure that you are working with a tensor processing unit, and to change your runtime type, you can go to Runtime in the top bar, click the Change Runtime Type option, and change your runtime to a V2-8 TPU. Then click Save. Finally, you can click the Connect button in the top right corner in order to connect to this TPU. The reason we are going to be using a TPU in this lab is due to certain incompatibilities with the built-in Google Colab T4 GPU. If you are unable to connect to a TPU or you reach the usage limit for this TPU, you can use a CPU as your hardware accelerator. However, note that while using a CPU, the code will take about 2 times as much time to run, so make sure that you are unable to connect to a TPU before resorting to the CPU. Now, let's download all of the dependencies and packages we need to go through this lab. First, we're going to import TensorFlow and install it so we can work with tensors or multidimensional arrays. Then we're going to install a library called OpenCV-Python, or CV2 for short, as a dependency for the MIT Intro to Deep Learning package. OpenCV is a framework that is specifically built for computer vision tasks like ours, and it will aid us in the image processing. Then we're going to install and import the MIT Deep Learning package, which was created by the instructors of the course to help support their labs. And finally, we're going to import the matplotlib package for graphical visualizations, the NumPy package for NP arrays, which are highly efficient multidimensional arrays, and TQDM for built-in textual progress bars. Now, all of these packages are going to take about 2 to 3 minutes to download, so while it is importing, I'm going to go through the MIT Intro to Deep Learning package. The MIT Introduction to Deep Learning package was created to have several built-in functions to abstract away some of the more complex coding parts of our lab so we can focus on the deep learning experience. For Lab 2, we have 2 functions that allow us to visualize all of the predictions from our model on our testing dataset. So first we have the plot image prediction function, which takes a given array of prediction probabilities, the true label or type of an image, and the image itself. This will allow us to plot a prediction of the actual prediction versus its expected output, so we can see if our model correctly predicted the image for its classification. Second, we have the plot value prediction function, which does a similar task, but now also has a bar chart, which allows us to see the different probabilities of each model, depending on if it classified the image correctly. So now that all of our packages are done importing, let's go into the MNIST dataset. The MNIST dataset contains 70,000 images of the handwritten digits from 0 to 9, and all of these images are grayscale. This means that each pixel in each image contains a value from 0 to 255 to represent how white or black it is. Our 70,000 images are split into a set of 60,000 images for training, which are going to be fed to the model, and 10,000 images for testing to see how our model performs after training on unseen data. Each image contains 28 pixels by 28 pixels. Now, let's download our MNIST dataset from TensorFlow, including the training images and their labels, as well as the testing images and their labels. For the training images, we can use the np.expanddims function in order to convert our training images to a numerical representation in a high-dimensional space so it can be compatible with our model, as our model will not understand colors or images directly. Then for the training dataset labels, which are the digits from 0 to 9 for each image, we can convert these labels to an integer type, so that way our classifications are outputted as an integer from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Then we are going to do the same for our testing images and their labels, converting the images to a numerical representation and computing our labels into an integer format. So now, let's plot some example images from our training dataset as well as their labels. We're going to select 36 random images from our dataset, and for each image, we're going to show the image itself as well as its label. When we run this code, we can see that we have all of our digits from 0 to 9 in many different thicknesses and handwriting styles, giving our model a diverse dataset that it can train on to understand different handwritten digits. Now, let's start by building a simple neural network that takes an example image of size 28 by 28, which is two-dimensional, and turns it into a one-dimensional representation with 784 input neurons, and each neuron has its own input for each pixel. Then we can pass all of these values through a hidden layer containing 128 neurons, and finally take those outputs into a final dense fully connected layer containing 10 neurons, one for each of the probabilities of the image being from a digit from 0 to 9. So 0 will have its own probability, 1 will have its own probability, and etc. until 9. So now let's build this neural network architecture in code. We're going to use the sequential API from TensorFlow, which allows us to chain several layers together simply. We're going to start with a flatten layer, which will allow us to create our two-dimensional image and turn it into our one-dimensional vector with 784 inputs. And then we're going to use a dense or fully connected layer with 128 neurons and an activation function of ReLU, or rectified linear unit, which is extremely common for image classification tasks like ours, as it is a very simple and efficient function that also introduces nonlinearity into our network. Finally, we have our second dense layer, which has 10 neurons and an activation function of Softmax to take all of the outputs and turn it into a probability distribution where all probabilities sum to 1. Note that while you are trying different training parameters in our training process, you will need to rerun this block of code in order to reinitialize the model so previous training does not affect the new training that you have with your new parameters. Now let's use the .compile function on our model in order to create it with a given optimizer, a type of loss, and different accuracy metrics. We are going to be using the optimizer called Atom, which introduces an adaptive learning rate for our model, and we're going to start it with a learning rate of 1e-3, which is equivalent to 0.001. Then we're going to use a sparse categorical cross-entropy loss, as cross-entropy type losses are very well suited for probability tasks like ours, and this specific type of sparse categorical is very simple and efficient. Finally, we will introduce the metric of accuracy So that way we can see the accuracy of our predictions for the model as well as the loss. So now that we have compiled our model using these specific parameters, let's train it on our entire dataset. First, we're going to define a batch size and a number of epochs. The batch size is going to be set to 32, which is the number of training images and their labels, which are put into the model from our entire training dataset at one time. And the epochs is set to 10, which is the number of times that we're going to loop through our entire training dataset. Now we're going to use these two variables on our model by using the .fit function, which is a very high level and easy way to train our model, inputting the training images of 60,000 that we have, the training labels for all of these images, and the batch size and number of epochs. And now we can run this block of code in order to allow it to train, and it will take about 1 minute to go through the training dataset 10 times. While it is training, I would like to go through a quick review of what we've done so far. First, we downloaded all of the dependencies and packages that we need for this lab, such as TensorFlow, and then we downloaded the MNIST dataset from TensorFlow and investigated some of the example images that we have, as well as their labels, to see what kind of data we're working with. Then we initialized our first simple neural network, which takes an image, flattens it into one dimension, and processes it in order to output the final predictions in a probability format. And then we created this model in code using the sequential API as well as TensorFlow's built-in layers. And we used the .compile function to compile our model using an optimizer of Atom for adaptive learning rates, as well as sparse categorical cross-entropy laws in order to train our model. Our model has now finished training in 51 seconds, and it has achieved a final accuracy on the training dataset of 99.57 and a loss of 0.0147. Now, let's see the accuracy that our model is going to have on the testing dataset. We can use the .evaluate method on our testing images and the testing labels to see the loss and accuracy of our model. When we run this code, we can see that the loss is about 0.07 and our testing accuracy is 0.979 or 97.9%. The reason that our testing dataset accuracy is lower than the training dataset is due to overfitting. This is why if you continue to experiment with the different parameters for batch size and epochs as well as learning rate, you will be able to see that you may be able to achieve a higher accuracy on the testing dataset depending on the parameters you use. So now we're going to take a step further from our simple neural network, and we're going to create a convolutional neural network. We're going to start with our input of a single image 28 by 28, and we will use a convolution with a 3 by 3 kernel in order to learn 24 different feature maps of size 26 by 26. Then each of these feature maps will go through a MaxPooling operation with a 2 by 2 kernel in order to decrease their size by half to give us our 24 feature maps, each with size 13 by 13. Then we're going to send these feature maps to a second convolution with kernel size 3 by 3, and we will have 36 feature maps with size 11 by 11. Then we will perform another MaxPooling operation with kernel size 2 by 2 to decrease these sizes by half and achieve our final feature maps of 36 with a shape of 5 by 5 each. Now that our feature maps are at such a small size, we can flatten them into one dimension to get a fully connected layer of 900 hidden neurons. Then we can pass these neurons through our second hidden layer, which contains 128 neurons similar to our first simple neural network. And finally, we have our final fully connected layer with 10 outputs, with each neuron being the probability for each of our digits from 0 to 9. Now, let's define this convolutional neural network in code using the sequential API. First, we're going to start with our convolutional layer, which is called conv2d, with 24 feature maps and a kernel size of 3 by 3. Additionally, we are going to use a nonlinear activation function of rectified linear unit, or ReLU. Then we will take the outputs from this convolution and send them through a MaxPool layer by using MaxPool 2D, and we will set the pool size to 2 by 2, meaning the kernel size is 2 by 2. We will do something similar for our second convolutional layer, where we will have 36 feature maps, a kernel size of 3 by 3, and activation function of ReLU. Then we will again use a MaxPool operation with kernel size 2 by 2 and get our final flattening layer in order to turn this 2D output into one dimension. And then we can pass this one-dimensional layer through our dense layer of 128 neurons and a nonlinear activation function of ReLU, and finally get our Softmax final dense layer with 10 neurons, where each of our digits will have a probability and all the probabilities will sum to 1. Now we can build our model and pass a single input through it in order to initialize it and look at our model's .summary to see what it looks like. Our first convolutional layer has an output shape of 1 by 26 by 26 by 24, where each of our feature maps out of the 24 are 26 by 26. Then our first max pool is going to be 1 by 13 by 13 by 24, for each of the feature maps being decreased by half in size. And similarly, for our second convolutional layer, we'll have 36 feature maps of shape 11 by 11, and the max pooling will take this into half, giving us an output shape of 1 by 5 by 5 by 36. Then our flatten layer will multiply all of these together to get a 1 by 900 output shape, and we will pass it through our dense layers to get an output shape of 1 by 128, and finally 1 by 10 for each of our probabilities. Now, just like before, let's train and test our convolutional model using the compile, fit, and evaluate methods. First, for the .compile method, we're going to use the Atom optimizer, now with a learning rate of 5e-3, or 0.005. Then we will also use the sparse categorical cross-entropy loss, which is simple and efficient, but also useful for our probability task, and we will also log the accuracy in addition to the loss. Now, we are going to use a batch size of 32 and a number of epochs by 5, as I noticed that when you set it to higher, we start to overfit our model, and the testing loss and accuracy start to decrease. So now let's use the .fit function for a batch size of 32 and an epochs of 5 for our training and images and labels. So this will take another minute or so, and while it is training, I would like to go back through the lab and review again. So after we created our simple neural network, we noticed that it has an accuracy of about 99.5 on our training dataset, but it has an accuracy of 97.9% on our testing dataset. We decided to use a convolutional neural network in order to increase this testing accuracy so we can have better predictions. So we defined our convolutional neural network to have 2 convolutional layers with max pooling operations in order to achieve a better prediction probability distribution at the end for our output. We defined our convolutional model using the sequential API as well as the built-in layers of conv2D, maxpool2D, flatten, and dense to take our input of a 28 by 28 image and convert it to our 10 probability outputs. Then we use the .compile function with an optimizer of Atom for our adaptive learning rates and used a learning rate of 5e-3. Then we used a loss of sparse categorical cross-entropy, and we logged our accuracy in addition to our loss. We can see that already from the first epoch, our accuracy is about 93.3%, whereas before in our first epoch, we had an accuracy of 87.8%. This means that our model is definitely doing better from the start, but now let's track its progress as it starts to finish. We can see that across the next few epochs, the accuracy continues to increase to 98.45, 98.87, and now 99%. In our final epoch, we are achieving an accuracy of 99.12%, which is slightly lower than our accuracy finally from the simple neural network, but we will be able to achieve a higher accuracy on our testing dataset. So now our model has finished training with a final accuracy of 99.11% and a final loss of 0.0290. Now let's use the evaluate method for our test images and test labels to get our loss and accuracy on the testing dataset. We can see that we have our testing loss of 0.089 approximately, as well as a testing accuracy of 98.25%. This is already an increase of 0.35% from before, which is extremely drastic for such a dataset as our MNIST. Now, let's examine the predictions that we achieved using our convolutional neural network. To do this, we can use the .predict method on our testing images to get all of our predictions. Now, let's examine the distribution that we get for our first prediction. It is an array containing 10 different values, and we can see that all of the values except for the eighth one are extremely low. This is because the first probability is at index 0 for the digit 0, and so on for index 1 at 1, 2, 3, 4, 5, 6, and now at 7, we have an extremely high probability, extremely close to 100% confidence that our digit is a 7. So now let's see that the .argmax function from NumPy will be able to take our predictions list and get the highest probability in which index it is at. And when we print this, we see that it is indeed the digit 7. So now let's verify and see what the label for our digit was from our actual testing dataset, as well as what the image itself looks like. We can see that indeed the label for our digit is a 7, and the image itself is a 7 in the approximate shape. So now let's examine more of the predictions that we have for the first 500 images. When we run this code block, we can use the MIT deep learning package's built-in functions to view our 7 from before, which has 100% confidence that it is indeed a 7. If we look at some more examples, for example, index 100, we can see we have the digit 6 predicted at 100% probability of 6, and at index 294, our 0 is 100% probability predicted to be a 0. Now, let's look at the first 20 images that we have, as well as their predictions and the distribution that they had in a bar chart to see if there are some instances where our model may be incorrectly predicting some of the digits. So we're going to have it a 5x4 table where each image is going to have its own entry as well as the bar chart next to it. When we run this code, we can see that for the most part, our model is 100% confident in its correct predictions. However, for some images, such as this 5, it was incorrectly predicted with 86% confidence that it is an 8, and for this 3, it was 55% confidence predicted to be a 7, and there is much confusion as a lot of the other bars are high, meaning that the model was unsure which digit this is. Again, I highly encourage you to go through the lab and experiment with the different parameters, including the batch size, epochs, optimizer, and learning rate, in order to see if you can achieve a higher testing accuracy and perhaps solve all of these problems that we have with very small inaccuracies. Now that we have covered all of the processes for training with the fit function, which is very high level, let's examine a more built-in and custom way of training our model. So first, let's rebuild our convolutional neural network to forget all of the previous training it had, and let's use our own function in order to train our model. First, let's start by defining a batch size of 32 and a learning rate of 5e-3, or 0.005, and let's create a list to track all of our losses during the training progress by using the loss history built-in function from the MIT deep learning package. Additionally, let's create a plotter called periodic plotter, which will continuously update as we are training to examine the loss trend based on this list. Additionally, we're going to be using the optimizer of Adagrad, which is similar to Atom, but has certain differences that allow its optimized adaptive learning rate to change more frequently, and we're going to use our learning rate of 5e-3. Then, if there are any previous progress bars that may exist from our training, we can clear all of them in order to use TQDM to track our training process. Now, for every single possible batch size that we have, meaning for our entire training dataset divided by the batch size, each index is going to take its own batch of training data and convert the images into a numerical representation inside of a tensor. And then we're going to use TensorFlow's GradientTape method in order to get the predictions from our convolutional neural network for the given batch's images and compute the loss using sparse categorical cross entropy, comparing our predictions against the actual expected outputs of classification. Then we can add this loss value to our loss history list and plot the periodic plotter in order to track the progress of our training. And we can compute the gradient, which is the derivative of our loss function, in order to get the gradients which will be used with the optimizer, as well as the model's hyperparameters, in order to go back to the model, change its weights slightly, so we can achieve a better, lower loss and a higher prediction accuracy. This code will take a few minutes to train, so while it is training, I would like to go through a final review of everything we've done so far. At the beginning, we started by downloading all of our dependencies and packages for our project, and we examined the MIT Deep Learning package more specifically. Then we looked at the MNIST dataset containing 70,000 images of handwritten digits, and we processed all of the images as well as their labels to be in the correct format for our model. Then we looked at some of these images as well as our label and saw that there is a very diverse dataset that we have to work with, meaning our model will be able to identify many different types of digits. And we started by creating a simple neural network that takes our image and puts it in a one-dimensional format. We built this neural network in code, and we trained it using the .compile and .fit functions, and we achieved a final training accuracy of 99.57%. Then we saw on our testing dataset, we had a lower accuracy of 97.96%, so we decided to implement a convolutional neural network instead of our simple neural network, which uses two different convolutional layers to achieve a higher accuracy. We built our CNN in code, and we saw how its output shapes from each of the layers transition to the next. Then we again used the .compile and .fit functions to train our model and achieved a final training accuracy of 99.11%. And we saw that on our testing dataset, we achieved an accuracy of 98.25%, which is higher than we had before on our simple neural network. Then we examined the predictions that we got from our testing images for this convolutional neural network, and we saw that for the first image, we correctly predicted that it was a 7 with extremely high accuracy. Then we saw that several other examples were also predicted with 100% confidence correctly, but then we saw that certain digits were incorrectly predicted and even sometimes with a very high confidence. So we decided to create our own training process that uses the GradientTape method built into TensorFlow to take a batch, compute the loss, and get a value called the gradients in order to see how we can improve our model and achieve a higher accuracy. Now that our model is done, we can see that we achieved a final loss of 0.029, which is equivalent to a very high accuracy. In conclusion, I highly encourage you to go through the lab yourself and experiment with the different types of models, optimizers, learning rates, batch sizes, and epochs in order to see which model and which training process allows you to achieve the highest accuracy on the training dataset. Again, to access this lab, you can go to the inspiredk.org website and click on the AI Program Labs button. This will take you to inspiredk.org's GitHub, where you can go to the MIT Intro to Deep Learning repository, the Lab 2 folder, and the Lab 2.1 Image Classification with CNNs and TensorFlow Python Notebook to click the Run in Google Colab link so you can go through the lab yourself and experiment with all the different parameters that are available. Thank you for joining me in this lab explanation video. Goodbye!